So here in this online lecture, we are going to study about sulfonation of benzene. So this is your benzene ring here, and you want to place the sulfonic group on the benzene ring, which is SO3H. So for that, you need to react it with H2SO4, sulfuric acid, and this is a reversible reaction. So let's talk about it in a bit detail. So when you have benzene ring and you go ahead and react it with H2SO4, this reaction is highly reversible. It depends upon the concentration of H2SO4. So H2SO4 should be highly concentrated for the reaction to proceed in the forward direction. Okay, so that's why I put the double arrows. So it can go back to benzene ring also. If you want to desulfonate uh, a benzene sulfonic acid, then you want to heat it and add water, dilute the solution. Okay, so we will talk about it. So first let me tell you here something about this product here. So when you react it with H2SO4, the benzene ring, so what happens, this hydrogen here gets replaced with SO3H. So this is electrophilic aromatic substitution. So SO3H is substituting for hydrogen. So this is an example of electrophilic aromatic substitution, and this product right here is known as benzene sulfonic acid, and H2SO is sorry, H2O is the another product here. Now I was talking about the desulfonation here. So if you want to go back from this product towards the benzene ring, what you need to do is, what reagents you need to do, add here. So this is your benzene sulfonic acid. You need to add water. I already told you. So and you will get the benzene ring. Okay. So you need to add water under the acidic conditions and heat it. Okay. Now let's talk about this reaction here from the point of view of Lee-Chatelier principle. So if you have benzene ring, you add H2SO4, it makes benzene sulfonic acid. Okay, so if you increase the concentration of H2SO4, okay, if you increase the concentration of H2SO4 according to Lee-Chatelier principle, your equilibrium will adjust in such a way so that it will want to neglect the effect of change that you are doing on the reaction. So when you're increasing this, so it will go more and more forward so that it can compensate for the increase of this. So more and more of product will be formed, so the reaction will proceed forward. So this arrow is denoting that when the reaction will proceed forward when you increase the concentration of H2SO4. However, when you go ahead and add more and more water to this reaction, so what will happen, so you're increasing something on the product side, so it will go back. Okay, it will proceed in the backward direction so that we can neglect the change of this increasing water here. So more and more reactants would be formed. Okay, so this, it will go in the backward direction. So this is what the second point is showing. So when you increase the concentration of water, when you increase the amount of water, so what will happen, the reaction will proceed in the backward direction and you can have benzene as your product. Now moving on, let's look into the mechanism of sulfonation of benzene ring. Okay, so what do we need to understand from that is the sulfuric, we need to generate the electrophile. So these are the three steps you need to remember for any electrophilic aromatic substitution. So first you generate the electrophile, and then second you attach the electrophile on the benzene ring and it gets attached there. Okay, and then what happens is you get the carbocation on the benzene ring, and then you kick out the hydrogen. I'll show you with the steps. So carbocation is generated right here in as the second step, and then the third step, I'll just write it here. So you generate the carbocation carbocation on benzene ring, right? So I'll just draw it here. And then to restore the aromaticity, we react it with the base. Okay, so the third step is react it with the base. with the B here. So this will restore the aromaticity, and you have your electrophilic aromatic substitution. Now let's see here. So to generate the electrophile here, sulfuric acid, one of the molecule of sulfuric acid will react with another molecule of the sulfuric acid to generate the electrophile. Let's look into the mechanism now. So one of the lone pair of oxygen is going to attack on this hydrogen, which is very, very positive because it is attached to oxygen, which is very electronegative. So this positive hydrogen is attracting the attack from this lone pair of electron from oxygen. And what will be the result of that? So when it will go and grab this one, so this oxygen hydrogen bond will be broken, and it will look something like this. So H as double bond O here, double bond O here, and then you have this is O. So oxygen, and then there is another hydrogen here. So this hydrogen was already present, and this hydrogen is grabbed just now over here. And since oxygen lost a pair of electron, he will grab a positive charge. So I'm going to draw a positive charge on oxygen, and it has a lone pair. So the better way of writing is OH2. I'm going to write here OH2 here. So that was just for the understanding purposes. So oxygen has two hydrogens, one lone pair and a positive charge, right? So this is the situation of this one. And now what will happen here? So what it was going to do, so this oxygen has two lone pairs here. So I'm going to draw some arrow movements here. So if you have this OH2 here, so it is converted into a good living group, right? OH is a bad living group. It needs hydrogen, one more hydrogen. Oxygen doesn't like to be positive, so what it will do is immediately grab this electrons from this bond and leave from here, okay? And what will happen as a result, this bond will, these electrons will move here. So I will draw the result of this one, these moves. So what will happen, you will have S, this double bond O, this double bond O, this already left, so I will draw here H2O, okay? And then what will happen, this moved here, and making a double bond O here, so I will draw like this, and there is a H here, right? So this is the situation right now, and since oxygen used his lone pair of electrons to form this double bond here, so he will require a positive charge, and a lone pair of electrons is here, and I'm going to draw it like this here. So there is a electron pair here and the O here, okay? So this is how the situation looks like, right now. So I'm going to draw the resonance structure here for this one, so that you can realize we just obtained the electrophile here. So what is the resonance structure of this one? So what is going to happen is, um, this oxygen is going to grab this bond here, this one here. I'll just draw it like this. For example, it can get this because oxygen doesn't like to be positive here. So what do we have is, so this is a double bond O, this is a double bond O, and this is a double bond O, right? And then these are your electrophiles. So you have generated an electrophile here, okay, and you can go ahead and use this form also. So this is a neutral form of the electrophile, and this is your it is having a charge. So because this is a very, very strong acid here, because you can realize sulfur has the positive charge here, because sulfur is connected to three oxygens, okay, which seem to be very, very because they are very, very electronegative. So what will happen is, they will have these electron pairs drawn towards itself, which is making sulfur very, very positive. So you have a electrophile here, okay, And you can go ahead and kick this hydrogen out from here and draw the sulfur trioxide here, which is also fine, but to use which form depends upon the pH of the solution. So I will write here uh, pH of the solution. Okay, so if pH is less than pKa, okay, then what will you do is you will use this one because this is very very acidic. So you will use the first form here. I will just write the one here and write one here with it. And then if your pH is greater than pKa, okay, then you will go ahead and use the second form. So you need to know the pH of the solution. Let's say you have the question, just for the question purposes I'm telling you, and then let's move forward and do the reaction with this electrophile for this reaction here. So I have benzene ring here and this electrophile here. If we go ahead and draw its resonance structure here, so what we have is this thing as double bond O, as double bond O, and then you have this bond. If you move it here, let me draw it. Then you have this thing O and H. Okay, so now sulfur bears the positive charge here. Okay, so sulfur is attached to three oxygens, which is making it highly electron deficient, making it a very good electrophile. This is the resonance form of this one, where S is bearing the positive charge. Now let's do the attack of benzene ring. So here the pi bond over here. We'll go ahead and attack on this sulfur, and what will happen? This pi bond will move here. Let's go ahead and write the result of this one, because you know this is electrophile, and the benzene ring would like to attack it. So the aromaticity is broken here, and then what we have is one hydrogen here, and this will go ahead and attach here the electrophile. So what we have is S double bond O double bond O, and then you have this will be simply OH because it grabbed the electrons from this bond. So you have OH here, and then so we do realize here that there is a positive charge on this carbon here. So let me draw it in this way. We have a positive charge. So this carbocation um, is existing here. So you know the next step. So we will react it with the base here. Okay, with the base. This is a general base. So in your this case, you have which base? So water was produced. You know that. So I'm talking about the bases here. So water was produced when you reacted two sulfuric acids, and this can act as a base. And then also your HSO4 negative ion was also produced when two H2SO4s 4 reacted. The molecules of sulfuric acid reacted. This ion was also formed. So you can use either of them to restore the aromaticity of this benzene ring. So what will happen next is you will this base is going to attack and grab this hydrogen. So this hydrogen will be grabbed by this base, and what will happen? And this will be restored. This bond will be restored back, right? So let's go ahead and write that the result of this thing, these movements. So here's your benzene ring. This bond already existed. This bond already existed, and this bond just moved right here. So aromaticity is restored in this step, and you know this would be highly favored step because aromaticity makes the molecule extraordinarily stable. Now what about this one? You have S double bond O double bond O, and then you have this OH here. So you have successfully substituted the hydrogen over here with this group, which is SO3H. So I'm gonna write this is benzene sulfonic acid. So you have produced. We have done the sulfonation of benzene ring. Okay. Now we are going to talk about the desulfonation mechanism of benzene ring. So I will write mechanism of desulfonation. So what we have here is your benzene ring with your SO3H group here on the top. So I'm going to draw that. So S double bond O here, and OH group here. So it is going to react with water. So we already told you in the beginning that you need to add a lot of water, and we understood why we want to add water here in this reaction, so that we can remove this SO3H group here from the benzene ring and resume the benzene ring. And also you need to add it, you need to add the heat, and we will understand how and when. So what will be the thing here? So your oxygen here has two lone pairs of electrons, and this hydrogen here, you can understand this is very very positive here. So what will happen, this will try to grab this bond here, and because this is very very positive, so oxygen would like to go ahead and attack here on this hydrogen here. So let's write this result of this movement here. So you have your benzene ring, and then you have your double bond here, and then what is the result? So you have S double bond O, double bond O. Since this oxygen lost the hydrogen and grabbed this one, so this oxygen will have a negative charge, right? And then what about this this water molecule who grabbed this hydrogen? So I will go ahead and write that one also. So you have this oxygen here, and it had two hydrogens attached to it like this, and it recently grabbed one more hydrogen here like this, and since he used his own electron pair, so it will have a positive charge. So I'm going to write plus here. Okay, do you understand until here? I hope that's fine. Now what will be the next step here? Now, in the next step, what will happen? This double bond will act as a nucleophile. It will go ahead and attack here on this positive, on this hydrogen here. I will show you how. So this double bond will go ahead and attack here, and what will happen? This oxygen will try to resume this bond because oxygen doesn't like to be positive, so it will immediately grab this electron pair. This hydrogen H positive is freely available. This double bond will go ahead and attack, and I'm going to write the results of this movement here. Mm, this is the result of this movement here. So it went ahead and attacked here. Okay, and then what you have is this bond get break. Okay, so this bond is broken here, and then you have a positive charge, and you no, it grabbed the hydrogen from here, and which is attached here. So you have on the benzene ring this hydrogen from here, and this SO3 negative ion group, and there's a carbocation generated here, right? Now this is where you need the heat. So yeah, we'll draw this arrow and write the symbol of heat here. This SO3 group has a boiling point. It evaporates at, it has a BP boiling point of 45 degrees Celsius, and when you will heat your solution at 45 degrees Celsius, so what will happen? SO3 will leave as a gas. Okay. Now, when you heat solution at this point, so what will happen? So I'm going to draw the benzene ring here. Sorry. So I'm just going to use the format I'm using in this mechanism, the double bonds here. Okay, and then you have your H here, and then you have S. So what this oxygen is going to do here, this oxygen, it's going to use its one of its lone pair, okay, to form the double bond and thus making this carbon sulfur bond to break. So this bond will be resumed here in the ring as a double bond and regaining the aromaticity. And here you have hydrogen. Okay, so what will be the next step? So when you heat it, so what will happen? You will get rid of this carbon sulfur bond and this SO3 will be leaving and this one will come back as the double bond of the benzene. So thus you have the benzene ring here. So this is the mechanism for desulfonation of benzene.